So let's get pretty soon here to the actual rigorous definition of a limit. The key, I'd say, is really these two words in our proposed, still pretty vague definition. Arbitrarily close. Eventually, a sub n, to say that the limit of a sub n equals 0, still think about this example, we want to say that eventually a sub n gets arbitrarily close to 0 and stays there, and that's important too. And that's arbitrarily close is the key. And I want to make that a little bit more wordy, okay, because I think people have a hard time coming up with what that would mean carefully and come up with a definition that really turns out to work. I'm going to say eventually a sub n gets close enough to satisfy any customer. So let me explain that. Here's a metaphor I like to use with limits. Actually, mathematics in general, but especially with things like limits. So that's our replacement. Eventually, a sub n gets close enough to satisfy any customer to 0, or close enough to 0, I guess, and stays there. So I presented one customer to you at the end of the last video. This was a not particularly demanding customer who just wanted things to about 1 decimal place. So something around right here. What he did was he said, you know what? I don't really need this to be super accurate. If you can just tell me that these values, the a sub n values, the 1 over 2 of the n's, eventually get within 1/10 of 0, and usually it's symmetrical. Usually these customers are satisfied either way. You can make it asymmetrical, but the classic definition is symmetrical. As long as you can make sure and verify for me and prove rigorously that those a sub n's will eventually, there's some point after which they'll always be, always as in they will stay there, they'll always be between minus 1/10 and 10th, I'm satisfied for my purposes. Now, might be another customer. So I call that customer sometimes like the carpenter, somebody who is doing useful work but doesn't need incredible accuracy. Then what about the engineer or something like that who needs more accuracy? They're going to have a band that's maybe like minus 1 or plus 1/100th and minus 1/100th. I doubt you can see that very well. Okay, but basically sort of 2 decimal place, the 2 decimal place customer. So the still not incredibly precise engineer, but somebody who needs 2 decimal place accuracy. Can we satisfy that person with the same sequence? But perhaps with a different notion of eventually how long that person has to wait to get there. Almost certainly with a different notion of how long they have to get there. Well, this is true. Eventually, 1 over 2 to the n does become less than 1 over 100. It's always bigger than 0, so it's certainly greater than minus 1/100th. And in fact, that's going to be whenever n is greater than or equal to 7, because at 7 it's 2 to the 7th, which is 128. Okay, and so eventually, and there's a specific number we can attach to that, at term 7 or after, and no matter what after, it still works, 1 over 2 to the n is within this bounds of 0, these bounds of 0. Well, so you could have a definition that simply says, hey, there's a few customers we always serve. There's the 1 over 10th carpenter, there's 1 over 100th, and then maybe there's the really finicky person who requires that their calculations are always good to be within 1 in a million. That's just their rule. Okay. We can satisfy that customer. It turns out, if you look at powers of 2, if n is greater than or equal to 20, then that's going to work. And you could imagine a definition that says, look, practically speaking, we only ever get these kinds of customers. Nobody's ever more finicky than this. And I'm just going to say it's good enough if these values are always within the most finicky customer's bounds. Well, that's not how mathematics works. The way I like to say this metaphor is that mathematics exists to serve all possible customers with all possible degrees of finickiness. No matter how finicky they get, the rocket scientist who needs like 7 decimal places, or the number theorist who needs 100 decimal places to do some really finicky calculation about primes or something, or the advanced civilization from Alpha Centauri that needs 1 billion decimal places because they love incredible accuracy. Mathematics is supposed to serve all those people. And so that's what the any customer is going to be. So that's what we need to formalize. And the key is that first we're going to talk about which customer we're going to serve. That's going to come first in the definition, and that's usually what is a little bit surprising to people. We're not going to first talk about how long we're willing to wait and then say, oh, do I satisfy somebody? What we're first going to say is, today, which customer are we going to satisfy? Can we satisfy that customer by going far enough in the sequence to get inside their little bounds? And can we prove that? And then the key is that can we keep doing that no matter what customer ever shows up at our doorstep? So I think we're ready for the actual definition. Try to keep that picture. Okay. So here's the definition. And I'm going to phrase it in general, but you can totally think of, and I'm going to immediately go back to the a sub n is 1 over 2 to the n, and the limit is 0. Okay, we're going to say that the limit, as n goes to infinity, of a sub n is some fixed number, or some fixed real number L, if for every, and there's a traditional letter people use here, a Greek letter epsilon, greater than 0. You can think of that as standing for error, although I don't think that's historically exactly why it was epsilon. I was just looking that up and I forgot exactly where it comes from. For every epsilon greater than 0, that's going to be our error tolerance. And it's greater than 0 because it's like the distance between L and the one edge of the error bar. And making that 0, making that negative doesn't make any sense because it's a distance. And making it 0 would be that you have to be on the nose, and the whole thing about limits is you're approaching the right value, not necessarily ever getting there. Okay, for every epsilon greater than 0, there is some n. Oh, let me say some positive integer n. Let's see if I can fit this here. That is our waiting time. Such that one more quantifier. This is, you can usually tell the complexity roughly of a mathematical statement by how many quantifiers you need, and this is 3, and that's a fair amount. For every little n greater than n, we have a sub n is in within this person's error tolerance of the desired limit. So it's a bit less than L plus epsilon and greater than L minus epsilon. Period. And I'm going to tighten up how you say the algebra in just a sec, and it'll be more like what you'd see in a book. But this is it. This is the real thing. And let me just read it, but with the sort of notions of customers and error tolerance and everything. It says, no matter which customer we talk to, no matter how incredibly tight their error tolerance, as long as it's not absurd, meaning 0, there is some waiting time, which is going to be big N, and we're often not going to be super interested in really calculating that, but we might need to calculate it at least approximately to show that it really works. But often the point is you throw it away eventually as being too finicky. There's some waiting time such that after that waiting time, if I look at the terms in the sequence after that waiting time, and notice it's every n. So as long as I passed the waiting time, everything works after that. Everything is in the error bounds. That's the gets into the error bounds and stays there part. So as long as we're past the waiting time, all the values after that, every single one, should be within epsilon of the desired number L. So for example, here, this would be L equals 0. We'd be saying that those 1 over 2 to the n's are between minus epsilon and epsilon. For any epsilon, I can choose an n. Really, really important, super important, is that you can't do it in the other order. You can't just say, well, can I just figure out a waiting time and just say, you know, I'm just going to wait to A100, and that should satisfy everybody. No, of course that's not going to satisfy everybody. Look at how big A100 is, and choose epsilon to be smaller than that, and you're not going to satisfy that person at stage 100. So it's got to be in this order that you pick the error tolerance, and then you say, ooh, for that person, wow, epsilon is like 10 to the minus 2,000th. Wow, this person is really, really picky. Then you say, well, they're going to have to wait a long time, but we will be able to prove that even that person could be satisfied by, for example, this particular sequence. and that particular limit. Now, you'll often see this with a little absolute value inequality. It just makes it a few fewer symbols. It's the distance between a sub n and L is less than epsilon. And that's, you can think of it as distance on a number line. It's a great way to think the absolute value of the difference of two numbers. Or you can just say, hey, whenever I have the absolute value of anything less than some positive number, that just means that this number is between epsilon and minus epsilon. The difference, with the sign taken away, with the sign in other words, is between minus epsilon and epsilon. And if you just add L to everything here, you just recover what we had. Okay. So you can always think of it like that, but you'll often see it with the absolute values. That's how you most often see it. It's just a little tighter and is nice for certain manipulations. Okay, so we've got the definition. The next video will show that yes, the limit of a sub n equals 0. Give it just a little introduction to how would you prove this? How would you manipulate it with actual formulas? And then we'll go back to s sub n. Once we know a sub n, we'll tell s sub n will be great. And then we'll look at a few other famous examples of limits with the same notation.